Hey guys, it's Dude Chemistry back on the Food Chemistry podcast, and welcome to a special exploration of the science behind one of the world's most beloved beverages, coffee. I'm here to take you on a journey from the humble green bean to that aromatic brew in your cup, uncovering the fascinating chemistry that makes coffee so captivating. The morning cup is much more than a caffeine fix. It's a complex interplay of chemical compounds and reactions. We'll delve into the roasting process, explore the key compounds responsible for coffee's distinctive flavor and aroma, and examine how different brewing methods influence the final result. So, grab your favorite mug, settle in, and let's explore the chemistry of coffee. Our story begins with green coffee beans, the raw, unroasted seeds of the coffee cherry. The transformation that occurs during roasting is nothing short of remarkable. It's a dynamic process involving both physical and chemical changes. Physically, the beans lose moisture, expand in size, and change color. But the true magic lies in the chemical reactions taking place within. The Maillard reaction, the same reaction which we discussed in the last episode, the one responsible for the formation of caramel and the browning of the toast, is in play here. The sugars and amino acids within the bean react at high temperatures, creating hundreds of new aroma compounds and melanoidins, the pigments that give coffee its rich brown hue. Think of it as a tiny chemistry lab inside each bean. Caramelization of sugars also occurs, contributing to sweetness and deeper color. And at higher temperatures, we have pyrolysis, where larger molecules break down, leading to the characteristic roasted and smoky notes we find in darker roasts. This is why lighter roasts tend to be more acidic, retaining more of the bean's original characteristics, while darker roasts develop more bitterness and those intense roasted flavors as those initial compounds break down further. It's truly amazing how much science is packed into that one little bean of coffee. Now let's zoom in on the specific chemical compounds that contribute to coffee's unique profile. Of course, we start with caffeine, an alkaloid that stimulates the central nervous system, providing that familiar alertness. But caffeine also contributes to coffee's inherent bitterness. Then there are acids like chlorogenic acids, quinic acid, and citric acid. These contribute to what coffee lovers often describe as brightness or tanginess. Interestingly, the roasting process itself breaks down chlorogenic acids, which further explains why darker roasts, despite often tasting more bitter, are generally less acidic than lighter roasts. It can seem counterintuitive. And then there's the incredibly complex aroma of coffee. This comes from hundreds of volatile organic compounds or VOCs. These are molecules that readily evaporate and reach our olfactory receptors. Some examples include furfural, which gives a sweet almond-like note, glycol, which contributes a smoky quality, and 2-methyl isoborneol, which, if present in high concentrations, can impart an undesirable earthy or musty aroma. It's like a complex orchestra of aromas playing out in every cup. We should also mention trigonelline, a compound that breaks down during roasting to form aromatic pyridines, further enhancing the overall flavor profile. We've explored the roasted beans. Now let's talk about how we actually extract those flavors into our final brew. The key here is extraction, using water as a solvent to draw out the desired compounds. The goal is to extract the flavorful components and caffeine without over extracting bitter compounds or astringent tannins. Several factors influence extraction: water temperature, grind size, and brewing time. Hotter water extracts faster, a finer grind provides more surface area for extraction, and longer brew times, of course, lead to greater extraction. Different brewing methods utilize these factors in different ways. A French press, for example, uses a coarse grind at a long steep time, resulting in a fully bodied brew with more oils and sediment. Pour over methods, with their finer grind and controlled water flow, tend to produce a cleaner, brighter cup. And espresso, with its high pressure and very short extraction time, creates a highly concentrated and intense flavor. Finally, let's consider how we actually perceive the taste of coffee. It's not just about our taste buds detecting sweetness, bitterness, sourness, saltiness, and umami. The aroma of coffee plays a crucial role. When we drink coffee, volatile compounds travel up the back of our throat to our olfactory receptors. This is called retronasal olfaction and is essential for our perception of flavor. It's why when you have a cold and your nose is blocked, food tastes bland. So the aroma is really shaping our experience of taste. And importantly, everyone's perception is slightly different due to individual variations in sensitivity to different compounds and our unique past experiences. That is why people have such diverse preferences when it comes to coffee. We've covered a lot of ground exploring the fascinating transformations and complex chemistry that occur from the green bean to the final cup. We've touched on the Maillard reaction, the symphony of aroma compounds, VOCs, the impact of brewing methods, and the crucial role of our senses in perceiving flavor. So, next time you savor your coffee, take a moment to appreciate the science behind it. Experiment with different roasts, brewing methods, and origins to discover your own perfect cup. It's a whole world of flavor waiting to be explored. Thank you for joining me, and this is Dude Chemistry signing off the Food Chemistry Podcast, and see you all in the next episode.